Yeah, live streaming is working now. So, Satya, you can start.
Yes. Very warm good afternoon to all. On behalf of VCAN 2020, we welcome you for this session. The title of the talk is Printable Functional Materials for Electronics, Photonics, and Energy Applications. I'm really happy to introduce the speaker of this session, Dr. Weiping Wu. He is the George Daniels Lecturer in the Electrical and Electronic Department, University of London. Dr. Wei Ping Wu is a researcher and an innovator with background of electrical engineering, chemistry, and material science. He has published more than 40 papers with total citations of around 3,000 and an H index of 29. From 2013 to 2015, he has been working as a research fellow on nanophotonics and metamaterials, funded by EPSRC in the Optoelectronics Research Center, ORC, University of Southampton. Dr. Wu is the chairman of Chinese UK Group Society of Chemical Industry, SEI, and he's also the members of RSC, IEEE, MRS, OSA, and SPIE. With this very short introduction, I invite Dr. Wei Ping Wu to deliver the talk. Thank you.
Thank you very much. So could everyone see my screen?
Yes, yes.
Yeah, so firstly, I would like to thank for Professor Grace's invitation, and it's a great honor to speak here. So today, my talk is about printable functional materials for electronics, photonics, and energy applications. And my name is Wei Ping Wu. I'm the George Daniels at the City University of London. So I've been working under carrying out research in the UK for about 10 years. I came to England and joined the University of Cambridge as a research associate in 2010, working on 2D materials and graphene. After about 4 years, then I was appointed as a research fellow and project leader at the ORC, Southampton University, working on photonics and metamaterials. At 2015, I got my permanent academic position as a George Daniels lecturer at the City University of London, and I serve as a chairman of a Chinese UK group of the Society of Chemical Industry since then. So today we are talking about the functional materials for electronics and photonics. So nowadays, almost everyone on this planet are benefit from the high tech and like a kind of convenience offered by these electronics, mainly dominated by silicon technology, which also like a compound semiconductor like gallium nitride, gallium arsenide, silicon carbide, and so on. However, there are several major challenges for these established quite important technologies, like non-flexibility, limited to small size, and the lack of like a certain functionality, like pore structures and so on. So naturally, scientists and industry experts want to develop some new technology beyond these traditional semiconducting electronics. So then a very important area, so-called flexible and printed electronics, has been developed since about 20 or 30 years ago. So these has been pioneered by the concept of the idea of developing flexible materials, electronic materials, and flexible electronic devices and systems, such as touchscreen sensors, flexible electronic papers, flexible solar cells, and smarter wearable textiles and flexible sensors. So if we're looking back through the development of electronics since the 1960s, actually, so the recent roadmap has been created by industry such as Intel. So the silicon industry has been pushing the physical dimension of silicon transistors very hard, and successfully pushed towards nowadays around 10 nanometer, even could reach even smaller. But it become much harder and harder. So the Moore's law is continuous, but the technology is hitting this kind of ceilings regarding the physical dimension. So quite early stage, from decades ago, then there have been researchers and proposals on using like a molecular level and a very small scale nanostructures for devices, including carbon nanotubes, nanowires, and two-dimensional nanostructure and molecular electronics. So actually, also this area is to do with the discovery of conducting polymer by Professor Alan Hager and Professor Alan McDonough and Professor Hideki Sarakawa, who won the Nobel Prize in chemistry in 2000 to recognize their discovery and development of conducting polymer. Actually, in early years, the main research focus has been on the conducting polymer, not semiconducting materials. But gradually, scientists realized that the fundamental physics can enable us to search a novel range of polymeric and organic materials, considering the conjugated carbon backbone structures that could delocalization towards this kind of energy band gap, such just very similar to inorganic semiconductor. But in this organic material, they are being called as a HOMO and LUMO levels. So in my research, since I have been a PhD researcher, I've been working on these conjugated molecular devices, mainly focusing on transistor devices. So if we're looking at organic transistor devices, then we can see that there's it is a multi-layer structure. And because it's an emerging kind of electronics or as a transistor as a key device, so this type of device can utilize a wide range of materials. For semiconductor, for instance, for semiconductor layer, we can using like a nanocarbon material or organic semiconducting material, and we could also replacing the traditional oxide dielectrics with polymeric or hybrid like dielectrics. Then, in addition, for electrodes, then both metallic and carbon and conducting polymers have been used as electrodes. So during my research, one part of my research is on the development of novel materials by a chemical approach. So two widely or most important chemical reaction methods have been applied are the coupling chemical reaction. One is called the Suzuki coupling, the other is called the Steele coupling. So this slide shows some examples on how this kind of conjugated structure can be synthesized by a chemical or bottom-up approach. So then after the synthesize, then due to the high demanding of this purity of these organic semiconductors, then these materials need to be purified carefully by either by solution process or by vacuum vacuum kind of crystalline process to enhance their purity, so that you can gain a optimized mobility. So so during my PhD research, I explored a wide range of pi conjugated molecules with fused rings. Then discovered that this particular class of material show a very impressive mobility and transistor performances. So then these are just a couple of examples of the research output I achieved, for instance, like organic transistor, organic memory devices, organic photodetectors, and organic nanowire transistor. So then actually this type of materials can be classified as small molecules or polymers.
Dr. Ethan, sorry to interrupt you. We are still
Sure.
seeing the first slide. Your slide is not.
Can you see now?
No, still we are seeing classical
First
electronics
slide.
and photonics. Yeah.
But I'm moving through my slides. Let me try to. Can you see now?
Not yet.
Okay, so let's yeah, it says screen sharing has failed to start. So there's some technical problems.
Okay, maybe you can just close and then
Yeah, I will restart.
please.
Hello, everyone.
Yeah.
Hello, sir.
Hi. Can you see my screen now?
Yes, yes,
Yeah,
yes.
yes.
Is it moving to a, sorry. Wait a moment. Now, how about now? Can you see my screen?
Now we are seeing your screen first. Title slide. Yeah. Now it looks fine. Can you just move on to the next slide? So that,
Yeah. Is it okay now?
now we are just seeing the title slide.
How about now? I move to the second page.
Yeah, it's second page now.
Yeah, yeah. Okay, now. Shall I restart again or shall I? Okay, I will briefly.
You can continue with very left, please.
Okay, so I So I just was introduced in the background about the flexible and the printed electronics. Then this roadmap developed by Intel and indicating
Sorry to interrupt
that
you. We are just seeing the video, not the screen.
no screen. Okay, just a moment. Hi, can you see my screen now?
Yeah, it looks fine. Yeah.
Yes.
Yeah, you can go
Hi.
ahead.
Yeah, sorry. Apologize for that. So I'm waiting. I'm talking about this flexible printed electronics, and I then I have I have talked about the background of my talk. So it's about the conventional silicon-based or inorganic-based electronic has some limitations, such as poor flexibility and limited small areas. So during my PhD, I did some research on the conjugated molecule, which actually has a strong link with the Nobel Prize discovery on the conducting polymers. So gradually, scientists realized the necessity of developing these conjugated materials through the concept of localization, and this conjugated organic material could form the band gap, and then we define them as a homo and LUMO levels. So for transit devices, then it consists of a wide range of materials, and the most important layer is actually the semiconducting layer. So we actually have developed these organic materials by two important coupling chemical reaction. So the first type is called Suzuki coupling, and the second type is called steel coupling. So in my PhD, I did a lot of research, and I have synthesized a wide range of materials, talking about hundreds. Then it's a large amount of work, but I feel that it's very excited to see a lot of amazing materials by molecular engineering. So from the chemical synthesis point of view, then we can tailor the chemical structure. And in particular, I summarize that, I conclude that the pi conjugated molecules with the fused rings have enhanced performance. So after synthesis, then we could fabricate a wide range of organic devices, including organic field effect transistors, organic memory devices, organic photodetectors, and organic nanowire transistor, and so on. So these materials can be classified as the small molecular materials, polymers, and so on, which show very promising or encouraging performance regard to the mobility that is comparable to the amorphous silicon. But yet they could be solution processed by inkjet printing or spin coating or large area printing and so on. So then, for instance, we have found a very interesting class of extended TTF molecule, which has been sort of synthesized, but with as you can see from this slide, it's called BTTF. Then it's a kind of a 2TTF molecular structure, like being coupled with a benzene. So this structure has this type of very strong pi-pi interactions, and this small molecule, they tend to crystallize into crystals. So you can see this kind of fine crystal ribbons at the channel of the two gold electrodes. However, we found that this, although we got a relatively high mobility, but this from this output characteristics, we found that it has very poor on-off ratio. So we've been very curious on the reason why it has a relatively low on-off ratio. So we have solved this problem through two approaches. The first approach is to blend with a very low mobility PBK molecular or either insulating kind of polymers. We successfully enhanced this on-off ratio and get the nice kind of optical curvature with sortation. Then we further redesigned this type of molecule by attaching this pi electron withdrawal functional groups at the two ends by learning from this famous kind of naphthalene bismuth and this perylene bismuth molecule, which is a red dye industrialized by Bosch company in Germany for decades. So by this approach, then we have successfully get a very high mobility and a very high off ratio organic field effect transistors. And this crystalline structure indicates that this material have very strong pi-pi interactions within this molecule. So similar to inorganic material, then this material can be designed to be p-type or n-type or ambipolar behavior, which actually can support both electron and hole charge transportation. So in addition, there's some very interesting molecules like metallic containing like polymeric materials that can show impressive molecular charge transportation and high off ratio for transistor devices. So along my research, I also have done some research on these molecular or single molecular transistors and single molecular junction devices, which trying to push in the limit of these electronic devices beyond the Moore's law. So the dimension is here talking about 1 nanometer or very short channels and so on. So I wrote a book chapter invited by the United Nations Education, Scientific and Culture Organization. So during my research, another piece of my work is growing these single crystals of this pi conjugated molecule. So I obtained very beautiful single crystals from the arens or tentorins and the pentancy. Actually, during my research, also I found some like black spots in this pentancy single crystal. Then actually they are sort of thermally converted into some graphene-like structure. Then when I think about this kind of links between these organic molecules and carbon materials, then we can see that from these slides, which I found from this Bristol University Chemistry Department web page, is that actually C60, which Fluorine, or C70, or so-called carbon clusters can all dissolve in these solvents. So inspired by the idea, then I started very interested in graphene. Actually, as everyone knows nowadays, it's a Nobel Prize funding. So the relationship of graphene and this carbon nanotube and this C60 has been summarized by GAN and at the Nature paper. So then actually we can regard all these or most of this carbon material can be modeled by this single layer graphene. So for instance, the C60 or carbon nanotube or graphite, or even our small molecular like pentancy, actually can be regarded as part of this kind of graphene structure. Then in addition, actually this type of carbon material can be classified as 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional material. So the game's discovery actually not only on finding or synthesize or prepare the graphene, but also on realize that graphene is a very interesting physics platform, and they found a very interesting condensed matter and this spin behavior of graphene single layer material. So that is the main contribution leads to their Nobel Prize in physics. Then following that, since 2010-ish, then actually there's a global kind of gold rush on this kind of graphene research. So if we're looking at the preparation method of graphene, we actually will know that it's actually quite easy to prepare single layer graphene by graphite and Scotch tape. But the limitation is that it's quite difficult and time consuming to prepare single layer graphene. So the more advanced method has been developed by the Cambridge University and other research groups working on CVD growth of graphene and 2D materials. And nowadays, it's possible to grow this graphene and 2D materials at a wafer scale, talking about the 8-inch or even meter scale. So during my time at Cambridge, I had worked on this actually stacking or transferring CVD graphene onto the cold substrate to form multi-layer and a few layer graphene on the cold substrate by repeat. It's very simple process, just the stamping and the repeating. So we used this graphene or multi-layer graphene as this kind of cavity RF devices that leads to some metamaterial research. I'm today going to talk more about the preparation of graphene using solution process. So this slide summarizes the various methods to prepare graphene. So one fundamental challenges are questions how to obtain high quality graphene at a low cost and high volume, high amount. So actually, the only choice tend to be the chemical or the liquid phase exfoliation. So here we have been using very low cost starting material like graphite and the solvent. Then we have been using a sonication, like bath sonication, which is the same facility to wash our glassware and in the lab, and then after mixing with the solvent and the sonicate for 10 hours, so we're using centrifuge to isolate the graphene from this unexfoliated multi-layer graphene flakes. Then we can get the ink at a high quality from very small amount, like 1 ml to 20 ml, then to liter scale. So this ink development is a very universal and powerful, and then can be applied to other 2D material like MOST, WST, polonitride, and so on. So once we got the ink, so then we can using the inkjet technology to print and to pattern this graphene material onto the substrate. Then this actually could helping us to fabricate electronic devices on the flexible substrate like the paper or PET and other bendable substrate. So during this fabrication, we found that this type graphene actually, due to its hydrophilic nature, so it's difficult to directly inject on this substrate. Rather, the substrate needs to be kind of treated with a kind of silence and so on. So after a range of comparison study, we have found the optimal condition, and we successfully inkjet printed the graphene as well as a graphene covered with conjugated polymers, polysiphon, which is PQT12. So we have demonstrated a very high mobility of graphene transistor, but still very low on-off ratio due to the zero band gap nature of graphene. Then a solution has been proposed by mixing PQT12 with graphene to gain improved on-off ratio. And this method and this piece of work has been extended to MOS2 and WS2. So then if we compare about this method and with like graphene oxide, which actually induce a high level of kind of defects, and also the price to grow the CVD graphene on wafers. Actually, this approach is very promising and very encouraging towards the industrialization. So I spent some time and effort on produce these graphene inks and the graphene material at a larger scale. So then working with some spin-off companies, small MCME in the UK, and we got some Innovate UK funding support to move this area further. So then this slide shows the limitation of graphene oxide. Although it's a amazing material for certain application like composites or batteries, but for highly conductive applications, the graphene oxide can only achieve this kilo ohm square conductance at 80% of transparency. So at Cambridge, I've been proposed a new method on attaching these metallic nanoparticles to this graphene that is exfoliated not from geo but from graphite. So in aiming to enhance the graphene's conductivity for this like transparent conductors and RF device applications. So this method tends to be very effective. So this by roll coating method, this graphene transparent conductor shows a very low heat resistance around 50 ohm per square at transparency of 90. And this piece of work has been published at the Nature Graphene Conference in 2011, and also a graphene conference in Brussels in 2012. Based with these highly conductive transparent conductors, smart window devices have been fabricated by liquid crystal technology. This is a comparison and some flexibility test using graphene. Then beyond that, then I've been moved to synthesize three-dimensional porous graphene materials through like plastic or biomass as a carbon source. Then we have been developed this technology in new application areas such as solar steam generation, and to kind of convert the seawater into drinkable water. Then due to the high surface area and the high optical absorption of graphene, porous graphene material, then we can gain a very high temperature at surface of the water, and the evaporation rate has been reached the water record. And another advantage of this porous material is it's a mechanical property rather than a kind powder-like nanomaterial. So this mechanical property is important because without a mechanical property, we can't apply any stress on it, or we can't blow it. Then because of this advantage, so if we look at the front cover of this advanced function material of that paper, it actually further demonstrates the utilize the wind energy onto this onto this type of device, which is only can be supported by the fact that this type of material has a superior mechanical property. So then, following that, I have thinking that why not like prepare a novel graphene or carbon material from conjugated polymeric structure. However, the early mentioned like the coupling chemical synthetic method tend to be quite expensive. So therefore, I choose the PVC, a kind of plastic that is being produced in millions tons scale every year of the world. So also it's potentially caused a lot of environmental polluting problem due to the halogen containing halogen elements inside this polymer. So therefore, I using PVC with KOH and DMF to mix it using mechanical grinding, and then the color actually changed from transparent to yellowish to brown or blackish, then indicating the formation of conjugated bonds inside this polymeric structure and the reaction of chlorine items with KOH towards KCl and water. So after high temperature processing, then we can get in the pure carbon materials without chlorine items. Rather, it only contains carbon, oxygen, and nitrogen. So then several related work is about the dimensional of the nanomaterial, about the 0-dimensional and 1-dimensional and 2-dimensional. So when we combine any of these material together, like 1D towards with 2D, then we can actually form this 1D and 2D composite structure, carbon-carbon composite structure. Then by electro kind of plating or reduction of graphene oxide, then as you can see from the SEM imaging, this graphene flakes has been successfully attached to the 1-dimensional mesh of this carbon nanostructure, micro and nanostructure. So this allows us to heat this pure carbon material up in the open air at a very low voltage, only requires 3 volts. Then it can heat up the surface of water at an incredible high temperature, around towards 400 centigrade. So this boosts up the performance of this steam generation of seawater. So again, has been enhanced the evaporation rate up to around 20 to 30 times, which is a major achievement in the field. So also, this carbon material has found an application for energy storage. So for this, of course, everyone or not everyone, so a lot of researchers, a lot of groups are working on supercapacitors or batteries. But actually, our particular type of graphene or porous carbon material has shown quite promising electrochemistry activity when we running some initial tests a few years ago. So then we have designed some very highly ordered kind of micro or nano structures of carbon material with hollow structure. Then this high surface areas carbon material can be used as electrodes for supercapacitors and has shown much enhanced performance as a supercapacitor electrodes. Then also with the philosophy of one-dimensional and two-dimensional, so I have successfully demonstrated high-performance batteries with a one-dimensional tungsten disulfide nanotube with a two-dimensional layered graphene material. So then they have a bit outlook of the future development of the optoelectronics. So actually, we also started from the functional material, either from a chemical synthesize approach or from a material science or physical approach. Then we use this material to fabricate optoelectronic devices, then seeking their applications as a system or healthcare or energy and photonics application or industry applications or environmental monitoring applications. But there's more efforts that is required at the device level and at the system and the practical implementation level. So here, this slide has an overview about functional material and 2D material and how they can be used to fabricate novel devices. And also, even looking more broadly, like actually this novel electronic material and optical material and devices can solve major challenges in this real world, such as healthcare, aging, and this polluting and the security and also on this advanced transportations and the securities and smart like machine human interfaces and so on. So I would like to thank my collaborators at the University of Cambridge, Professor Andrew Ferrari, Professor Dapin Chu, and Professor Bill Mill, and Professor David Penny at the ORC Southampton University, and Professor Nicola Joseph at Southampton University, and my supervisor, Professor Daoben Zhu, and Professor Yinqi Liu at the Chinese Science of Sciences, and my collaborator, Professor Bingyuan Zhao, and students at Shanghai Jiao Tong University, and Professor Robert Bradley at the University of Oxford. And I thank the funding support from ECS, APSRC, Innovate UK, GCIF, and George Dennis Trust, and some charities like this IUPAC and SCI. And also I thank Samsung and Natural Science Foundation China for support. Thank you very much. Thank you. I'd love to take a question.
Thank you very much, Dr. Wei Ping, for the wonderful talk. We have plenty of questions from the participants, but due to time constraint, we can ask a couple of questions. One question from Swati Yadav. What she has asked is, have you tried copper oxide as bottom and top electrode and PDMS or P3HT as semiconducting materials? So what kind of solvent you will be using for P3HT semiconducting ink?
Okay, sure. So for copper oxides, of course, it's a good idea, but usually it's using copper as a contact, either could be top contacts or bottom contacts. Actually, I have some work on using copper as low-cost electrodes for transit devices, but copper has some problem. Firstly, like the work function matching. Secondly, it's about this surface oxidation trend. So you probably need to engineer this surface using some like chemical reactions or using some treatment to enable to form almost contacts with this organic semiconductor. So for the solvents or P3HT, so actually a lot of researchers have been using the same material for photovoltaics, for organic solar cells. So the ideal solvents for this P3HT or similar polysilicon material are these chlorobenzene or dichlorobenzene. So because of due to this solubility consideration, also another fact to consider is the speed of the solvent evaporation. So I think a solvent choice is no problem, but you can play with the solvent choice by mixing the solvents or one or two solvents, or using some more green solvents, more kind of environmental friendly solvents. Also for inkjet printing itself, sometimes you may find it's quite annoying to using a chlorobenzene or dichlorobenzene to inkjet print, because it essentially will tend to dissolve the plastic parts or pipes of the inkjet printer. But it's a more technical challenge, and we can design a inkjet printer which is a solvent resistor. But maybe for the research purpose, you could probably need to search like more less aggressive solvents that will not dissolve your plastic. Thank you.
Yeah. One last question, finally. Can conducting polymers be employed in high-power UV-based devices, as UV devices suffers from heat issues? That's the question from one of the participants.
Yeah. So firstly, from material design point of view, then organic material can have alternable like band gap or this stability, depends on the chemical structure. So for instance, like our in industry, like a polyamide, like some polymeric material or polymer coating has a UV resistant capability. So definitely, if we engineer the chemical structure, we can enhance this kind of high power UV resistance. Then in addition, from a composite or coatings philosophy point of view, we can also introduce some like a high refraction index or UV resistant like a nanoparticle, like a titanium dioxide, which essentially will enhance this kind of UV resistance. But when you introducing another nanomaterial, you probably need to consider this kind of compatibility. Also, if you are using it as an electronic device, you need to consider the impact, the usually negative impact on the device performance. And in addition, you could consider using like a encapsulating layer, like you put a coating layer on top of the electronic device to seal your device. This not only applies to the high intensity UV device, but also even like photovoltaics, organic solar cell or other solar cell devices on the solar or kind of photo detect device, maybe, and it's a promising solution. Thank you.
Thank you once again, Dr. Wei Ping, for this wonderful lecture and wonderful presentation. Thank you for your spending your time, and we once again thank you that you accepted our invitation, and on behalf of VCAN 2020, once again thank you so much.
Thank you very much for the invitation. So any further question, you feel free to drop me a line through my email. Thank you. Thank you very much.
Thank you. Yeah, thank you.
Thank you.
Thank you.
Bye.
Bye.
So any further question, you feel free to